Okay, yeah, let's get started. Quick review about chapter 2. So chapter 2 we talk about determinant, and at the very beginning we said we want to calculate the determinant value because it will determine whether your n by n matrix is singular or not, and we have proved that. So determine A equal to 0 if only if A is singular. And the determinant we give it this recursive definition, where it's sum over some row or column. So here we are writing as first row. So we sum over the element of the first row times inner product with the cofactors. And the cofactor is you take this submatrix where you delete this row in the column, and you calculate the determinant of this matrix and times -1 to I plus j. Okay, so to take any row in the column and you go through the elements, and then you inner product the elements of that row column with the corresponding cofactors. So you can take any row in the column, do this, and get a whole bunch of smaller n-1 by n1 matrix, and you calculate its determinant. And for this determinant, you need to recursive. You need to pick another row in the column and do this expansion. Okay. Okay. So that's a cofactor expansion of the matrix. And as we say, you can expand it on any row in the column. So let's go to, I think it's here. Okay. So we start with the recursive definition of determinant is cofactor expansion, and then you can expand on any row in the column. Then some properties. So determinant of the transpose equal to the determinant of the original matrix A. Then if you are triangular, so either the lower side O0 or upper side O0, then you can just calculate the determinant by multiplying the diagonal elements together, because all elements will multiply by some 0. And because you can expand on any row and column, so obviously you have a row of columns as O0 and determinant is 0. Then we have this property that we use to prove. Okay, so maybe let's not talk about this. Yeah, so the high level property does this. Then we go on to prove how determinant change when you do some row operation. When you do row operations on your matrix. And so the proof, let's skip, but the result is that if we change two rows, then your determinant got a -1. And if you multiply by a row by alpha, then your determinant get multiplied by alpha. And if you add or subtract a row from another, then the determinant doesn't change. And here we write delta E because we think about calculating the determinant of the elementary matrix. And it turns out that the determinant of the elementary matrix operate on, so any elementary matrix operate on any matrix A. The determinant of this EA equal to determinant of your elementary matrix times the determinant of your matrix A. Okay. This is true. And this is actually more general. So later we prove two very nice theorem. So and from knowing how the elementary operation okay, yeah, and from here then we prove the theorem that we say. The most important theorem in this chapter is that A is singular if only if the determinant of A equal to 0. Okay. Just by doing the reduced row, doing the Gaussian elimination on A, and you can get a whole bunch, decompose A into a whole bunch of E and reduced row echelon form. Then you analyze how the reduced row echelon form do, what the reduced row echelon form is when when A is either singular or non-singular. Okay. And and we also learn how to calculate the determinant of A more efficiently. That is, you can decompose A into those elementary matrices and and maybe an identity. Then your determinant A is just the inverse of the determinant of those elementary matrices inverse 1. And in practice, you can skip the changing lead variable to 1 steps, and just do the row subtraction, addition, and the row swapping. So you turn A into a triangular form. Then you get so the determinant of A and determinant T will be related by a plus minus sign, where the plus minus sign determined by how many swap you do. And then determinant of T is triangular, so determinant of T is just the product of its diagonal elements. So this is a faster way to calculate determinant. You do Gaussian elimination on A and see how the corresponding determinant change. And once you get a triangular form, then it's easy to calculate. Okay. So for example here, so we have this matrix, and you do Gaussian elimination to turn into a triangular form, and then you can calculate the determinant of this triangular form easily is 2 times minus 6 times minus 5. And you know determinant of this equal to just minus 1 of determinant of this, so the determinant of the original matrix is minus 60. Okay. And finally, the second most important theorem of this chapter, determinant AB equal to determinant A times determinant B. And this we once again done by our elementary matrix analysis. And this is when your matrix is not singular. Then when this B is singular, we can do some singular analysis, say calculating the number of non-zero elements. Okay, and and here's the checklist. So we have the technical lemma that we use to calculate the determinant of the row addition and subtraction. And anyway, once again, elementary matrix, then elementary matrix has these 3 determinants, and those 2 big theorems. A is singular if only if delta A equals 0, and delta AB equal to delta A times delta B. And here is another review. So once again, so we can combine our new theorem with 1.522. So now we know more about singular matrix. So singular matrix, we say A is singular if only if A equals 0 has a non-trivial solution and A is not row equivalent to I. And now we have something more. So it's also if only if delta A equals to 0. Okay, so everything together. Okay, so that's a quick review of first 2 sections of this chapter. Any question? If not, then let's go to, okay, I think we will actually go to chapter 3 because we don't have much left in this chapter. Okay. But yeah, I guess we can talk a little bit about chapter 3, but the homework should be only chapter 2. Okay. So anyway, so let's go to 2.3. So we have some applications of the determinant. Okay. So first is we can calculate the inverse of obviously non-singular matrix using determinant. And the other one is you can solve Ax equal to B using determinant. Okay. Okay. So let's first see this inverse. Before going inverse, so we define this adjoint matrix. So adjoint matrix is a matrix. So you start with a n by n matrix, and you can define a corresponding adjoint matrix. And there is a matrix that's formed by all the cofactors. And okay, let's try this. Okay, so remember cofactors, they are these things. So you have an element, then the cofactor is minus 1 to the I plus j, and the determinant of this remaining submatrix. So you delete the row I and the column j, and you got a remaining matrix. So you calculate determinant of this, and you calculate determinant of this and times minus 1 to I plus j. And anyway, it's a complicated thing, but this thing we call it Aij. Okay, and go back. Oh yeah, yeah, so those are covectors. So this A11 is a covector of A11, and but this matrix definition will actually have a transpose. So the A21 is actually covector of the A21 is here. Okay. So it's kind of like getting a transpose on the locations. Okay. So it's A1 N1 is a covector of this small N1 here. Okay. And anyway, we had our very technical lemma saying that the ith row of A and the covector of jth row, the inner product together, then is either equal to determinant A if I equal to J, because that's just covector expansion on ith row, or it's 0. And it's 0, we spend quite a few time proving it. Okay? And yeah, so it's either determinant A or 0. And from this, then you can calculate so when we calculate A and the joint of A, then we see it has a nice diagonal form. Okay, so let's see a few lines. Okay, so maybe this element, so this 1 element of A times the joint A. So we have A11 times big A11, A12 times big A12, da da da. So that's kind of why we get transpose, because we want the row to inner product with columns here. Okay. So all the way to A1n inner product with A1n. Okay, so that's nice. And as we see, that's the first one is I equal to JC. And okay, but anyway, we write it here. So this should be determinant of A. And but what if we do this first row with second column? Then we have small a11 times big A21, then small a12 times big A22, all the way to small a1n to big A2n. And we see that it is I equal to 1, J equal to 2 here. And I not equal to J, so that should be equal to 0. And similarly, so yeah. So you can probably see whenever you have an ith row here and the jth column here, so the ij element here, when I not equal to j, then that is I here and the j here. Okay. So ij's element here is the inner product of the ith row and the jth column, and that should be I on this small a and j on this big A, and that should be 0. So we only left with diagonal element, and the diagonal elements are all these things with I equal to j. Okay. And as we said, that's determinant of A. So we have a diagonal matrix with determinant of A everywhere. And yeah, then we can take all those delta A because this is by scalar multiplication inverse. And yeah. So this is just determinant of A times your identity matrix. Okay. So yeah, so we see that this adjoint matrix is very close to A inverse, because we want something that when A multiplied by this matrix, we want to get identity. Well, instead we get determinant of identity, so we just divide by the determinant. Okay, so A times the adjoint of A equal to determinant of A times identity. Then you just divide both sides by determinant of A, because it's just a scalar, so you can really put it anywhere. So A times 1 over determinant of A times the adjoint of A equals to identity. Yeah. Okay. And yeah, so that's our result. A minus 1 is adjoint of A divided by delta of A. And you see that this formula only works for when determinant of A not equal to 0, and that's consistent. Consistent with we say that A inverse 1 exists if only if determinant of A equal not equal to 0. Okay. Any question about the derivation? We go through this really quickly this time, and then we go a little slower this time. But people understand. Okay. So I think this is called Kramer formula. And anyway, so we have a 2x2 example that some of you might still remember. So we have A, B, C, D. Then the covector matrix. So basically the adjoint of A before transpose. is the cofactor of A is D, and the cofactor of D is A. Cofactor of B is C, is minus C, and the cofactor of C is minus B. Then the adjoint is you take this as transpose, so it's DA and minus C minus B. Hopefully this is correct. So if I multiply this with A, B, C, D, so the first one is AD minus BC. Okay, that looks correct. So the 1, 1 element is AD minus BC, and the 2, 2 element is minus BC times AD, and the 1, 2 element is minus AC plus AC, that's 0, and the 2, 1 element is BD minus DB, so that's also 0. Okay. I guess we have the same example here. Forgot. Yeah. So here we are writing as A11, A12, etc. Sorry. I got this a little confused. So for 2 by 2, this is the Kramer formula. So adjoint of A look like this. And so we swap the diagonal A2 to here, A11 to here, and it's minus 1, minus 1. And you see when you and so your n minus 1 is 1 over determinant of this adjoint matrix, and we just check the multiplication. I guess my notation is a little better because ABCD is easier to say. Anyway, that's a 2 by 2 example. And so we have another example. Okay, now this is very complicated. So we want to calculate a adjoint of A of this 3 by 3 matrix now. Okay. So 3 by 3 matrix, we want to calculate this adjoint of A, and we want to calculate all those cofactors. And so we first write down the correlating cofactors before we do the transpose. So the cofactor of these two is this 2, 2, 2, 3 determinant. And cofactor of 1 is this 3, 2, 1, 3 determinant. And so we should write everything correctly. So for example, the cofactor of this 1 is this 1, 2, 2, 2 determinant, etc. So we have cofactors, and you see the minus 1s are on those I plus j equal to even numbers. So minus 1, minus 1, minus 1, minus 1. And so you can calculate all the determinants. So skip all the arithmetic. And it should get you these values, and then you can do transpose. So you swap the off diagonals. Okay. And finally, you calculate A inverse 1 as this matrix divided by the determinant. And we also skip calculating a determinant. Okay. I guess we can check really quickly the determinant. So you just multiply this with UA. So see the 1, 1 element, so you have 2 minus 7, 4 times 2, 1, 2. Okay, so that's 4 minus 7 and plus 8. So that's 4 plus 1 equal to 5. Okay, so the determinant is actually 5. Okay. And as we said, this is called Kramer's rule. And you have it's a different name. Sorry, I got things mixed up. Okay, so Kramer's rule is another thing, but it's really similar. Okay, so that was finding A minus 1, and now we want to solve for AX plus AX equal to B. And I want to solve A is equal to B for A non-singular, so we have a unique solution. And the unique solution, obviously we can have A minus 1 on both sides, so X equal to A minus 1B. But we have a little more direct formula here. So X is, so it's a little complicated here. A is n by 1, n by n matrix, and B and X are n-dimensional vectors. So yeah, so or like or another way. So B and X are like n by 1 matrix. Anyway, so B and X all have n values, and here we are writing out each component of X. So we are saying ith component X is determinant of this weird matrix AI divided by determinant of A. Okay. And determinant by AI is, so this AI is a weird matrix where we replace the ith column of A by B. Okay. And so maybe that's true, but we'll have an example. Okay. So yeah, so AI, look at this. So your A is this thing, and yeah, and we have ith column here. Okay, maybe let's do this. Yeah, so we have ith column here, and the AI is you replace it by the B vector. Oh, it's ugly. Yeah, AI is you replace it by the B vector here. The B is AX equal to B dot B. Okay. This B vector. So you replace the ith row column of A by this B, and obviously that's another matrix you can calculate its determinant, and yeah, then you divide by determinant of A. This is quite restricted, it only works for A non-singular. Okay, it's still pretty cool. Most of the time, hopefully your matrix is non-singular. So anyway, as we say, we can solve for X equal to A minus 1B. So by the previous thing, we know that A minus 1 equal to adjoint A divided by determinant of A. Okay, and 11 times B. So we just write down things and see how they go. Yeah, so determinant of A equal to well, just determinant of A is still here, and adjoint of A we write it out. So it has a whole bunch of covector here. Okay. How do I say this better? Oh, okay, it's annoying. Okay, and yeah, so we have adjoint of A here is whole bunch of covector. So this big S, and then we have B vector here, and this equal to X. And now we just, okay, so determinant of A is just determinant of A, so it's here. And now we look at the ith element of okay, so let's write a little more. So we want to know what's the ith element of X, right? So maybe I here, so we have xi. So xi by matrix multiplication rule, it should be the ith row here, right? So it should be the ith row here. This row, so no, I don't want to draw this. Okay, this row, and so by looking at this thing, this row should be A1i, A2i, to ANI, and the inner product with this B vector. Okay, so xi by the matrix multiplication rule should be this row inner product with this column. We talk about inner product anyway, and yeah, and yeah, so that should be B1 times A1i, and B2 times A2i, all the way to Bn times ANI. Okay, so we are just writing the number here, and now we go to next page, and we rewrite this thing. So we have the upper thing is B1 times A1i plus B2 times A2i plus all the way to Bn times ANI, right? And okay, so why is this the determinant of this AI? Is because if we do covector expansion here, so expand here. No, this one. So we expand on this column. Okay, and okay, so let's check. We actually got this, and so cofactor expansion. So it should be B1 times the cofactor of this element. So you delete the row and column. And so this is a little similar to our proof of lemma 2.2.1. So when you delete this B1, and you see the cofactor, but you are also deleting this whole column. Okay, so let's just send as a cofactor of this A1I here. Okay, right? Because the only difference between AI and A is this ith column. But when you expand on ith column, you always delete the ith column. Okay, so the cofactor of B1 on AI is same as cofactor of this A1I on A. Okay, so that's just big A1I. And similarly, when you do the cofactor of B2 on AI, and you delete this column, so that's just same as the cofactor of A on A2I. Okay, so that's just B2 times A2I. All the way to Bn. Cofactor of Bn is on AI is same as cofactor of AI ANI on A. Okay. So yeah, so you see the determinant of AI expand on this ith column is just this thing we write down. It's B1 times A1I, B2 times A2I to all the way to Bn times ANI. And yeah. So we prove our rule. So this thing is determinant of AI divided by determinant of A. And once again, A is non-singular, so you can write Han-Hsuan, and you can divide by a non-zero determinant of A. Okay. So just stare at this a little bit. Okay. I'm happy with this thing. Okay. Yeah, the proof is a little technical, but anyway, this is something you can just plug in and calculate. And yeah, so that's the 2.3. So we have two things. We have that we define this adjoint matrix, which turned out to be pretty useful. So is you write down the cofactor of A, and then you remember you do the. Okay. So once again, you need to remember you also do the transpose. So you write down all the corresponding cofactors, and then you need to do a transpose, because the ij indexes are inverted here. And then we have a formula for inverse of a matrix and a formula for solving Ax equal to B, all for when A determinant of A not equal to 0. So formula for A inverse is just this adjoint matrix of A divided by determinant of A. And formula for solving Ax equal to B is determinant of A divided is you have a determinant of this AI, where I is so I just think this should be right in here. Okay. So AI once again is A, but ith column replaced by B. Okay. And yeah, so you calculate the fraction of those two determinants. Okay. And I don't know, this doesn't seem too efficient actually, because determinants are a little hard to calculate, and maybe Gaussian elimination is faster. But this is a closed form formula. So it's nice we have a closed form formula, but I think about how to calculate it, maybe it's slower. Okay. Yeah. So any question? Okay. Yeah. Okay, as we said, if you have no question, then I will go to chapter 3. So let's see, how do I set up things? Yeah. So we finish all determinant, and let's go to a totally different topic. Actually cancel. Let's don't do that for now. And we have chapter 3. Chapter 3. Oh, how do I? No. Oh, here it is. PowerPoint slideshow. Okay. Yeah. So we spent a lot of time talking about determinant. That's for n by n matrix. And now I want to talk about total different thing. That's about vector space. So this is about vectors of whatever dimension. Okay, so what are vector space? And once again, vectors. So vectors for us are really just those matrices. So I think we start with defining vectors are those matrices that just have one column. Okay. So it's a n by 1 matrix. And we say okay, so we define the space within. Okay, so we are going into a bit of HO abstract algebra. Okay, so we define this space. This space is the set of all vectors of some dimension. So in chapter 1, we say we are defining this Euclidean vector space Rn. That's basically the set of all n-dimensional vectors. Okay, and this R is for real because for now, for this course, we are mostly dealing with real coefficients. Okay, and okay, so in chapter 1, we just have this definition, and now we in this chapter we will see that the vector space has a little more property on it than just being a set of all those vectors because we have some operation on it and some property on it. And anyway, let's get to, okay, so today probably mostly is a review, so let's get to some probably high school review about what do you think about vectors. And so why is this n-dimensional why is this n-dimensional n values we think it as vectors? So we go to this R2 example. So two-dimensional vector is is a vector on two-dimensional space. So for example, you have this. Well, so first we say we have this two-dimensional column vector, right? We say R2 is a set of all those x equal to x1, x2, and x1, x2 real number. And it can be seen as a vector on two-dimensional space, like this, okay? So in high school or even middle school, you will draw your vector like this. So you have a two-dimensional space, so you draw a two-dimensional plane, so maybe x1, xy. And then you have vectors starting from somewhere and somewhere. Okay? So maybe from 0 to x1 plus x2. So we can have a vector corresponding to this two value x1 and x2, and it's just drawn this. Is the vector that's from 0 to let's say this is okay. So we don't have xy, it's a little weird. So x equal to x1 and y equal to x2, like this. So it's a vector. And and in high school, we know that we can translate this vector anywhere on the plane, right? On the two-dimensional plane. And but if you start from any point a, b, then you will end up the point a plus x1 and b plus x2, and we think this is still the same vector. It's still this x1, x2 vector, okay? Because the change here is still x1, and the change here is still x2. Okay. So hopefully, so this we're not very rigorous yet now, but hopefully this gives you an idea why x1 and x2 is a vector. Because x1, so for this two-dimensional example, x1 will be the x coordinate of your vector, and x2 is the y coordinate of your vector. So you can see our set of all possible x1, x2 is a set of all possible vectors in this R2, which is just a plane. Okay? And yeah, so this is called a Euclidean space. It's basically a normal space that we are familiar with, where both x's give you real numbers, and yeah, and you don't have weird matrixing. Okay, and yeah. So for example, the thing we just say here, so we give a number the example. So maybe your vector is 2, 1, and you shift x direction 2 and y direction 1. And it can be a vector starting from anywhere and go by this 2, 1. Okay? Those are vectors. And vector have length. And here length is also, this is probably you learn in middle school. So the length you can calculate from Pythagorean theorem and Pythagorean theorem. And yeah, this is square root of x1 squared plus x2 squared. Okay. So this is x1, this is x2, and this is square root of x1 squared plus x2 squared. Okay, that's the length. I think we'll calculate length much later in this chapter. Okay, so for now, this is a quick review. And okay, now we go to a little more algebra. And algebra, I want to do operation on your vector. Okay. So we can multiply a scalar on a vector, and we just define this by our matrix multiplication rule. So multiply a scalar on our matrix, then you just multiply every element by alpha. Okay. So alpha x1 times alpha x2. So for example, your vector x equal to 2, 1. Then you multiply by -1, you get this -2, -1, get multiplied by 3, you get 6, 3, multiplied by -2, get -4, -2. And here are the examples. So x, then you can multiply by x minus, you can multiply by -1, you get this -x, and you can multiply by 3 or multiply by -2, then get those different vectors. Okay, so that's the first operation you can do. You can multiply by a scalar, multiply by a number scalar, alpha here. And the second operation we can do on a vector, or more like two vectors, is we can add them together. So you have a vector u and a vector v. So u is just whatever u1, u2, and v is v1, v2. Then u plus v in xy coordinate can be written as this. So the first coordinate will be u1 plus v1, and the second coordinate will be u2 plus v2. And here we have a geometric representation here. So this vector u has u1, u2, and we plus vector v as v1, v2. And then you see that the x coordinate should be the u1 and plus another v1. And y coordinate is u2 plus another v2. Okay. And so this is u plus v, and its coordinate is u1 plus v1 and u2 plus v2. And then yeah, we have this interesting thing, and this says that, and yeah, we can draw those diagram and see that, just geometrically see that u plus v should be equal to v plus u. Okay, so the yeah, and we can also have the subtraction of u and v. So we can have this w equal to v minus u, because u plus w will equal to v, etc. And okay. And then we can have a three-dimensional example where we now have xyz, or x1, x2, x3 here, and and then the addition is still similar. So x plus y, x and x here, y here, and then you have x plus y, and then you want to, this is probably x1 plus y1 on the first coordinate, and x2 plus y2 on the second coordinate, and x3 plus y3 on the third coordinate, etc. And let's just go to general, okay? Yeah, so we have two-dimensional and three-dimensional, and we just go to n-dimensional. So hopefully you can imagine, or we cannot draw. We can have n-dimensional space. Okay. So yeah, so it's really hard to draw n-dimensional space because we are familiar with R3 in real life. But anyway, we can mathematically write down this representation of n-dimensional space just by n-dimensional vector here. Okay? So we can just represent the n-dimensional vector space by these n numbers. So this is Rn. It's just a list of n number here, and then we have two operations that we want to do a lot. So scalar multiplication and addition. So you get whatever n-dimensional vector x1, x2 to xn, then you can multiply it with a scalar, so alpha times x. Then you got alpha x1 to alpha xn. And then you have two vectors, is u and v, then you can add them together. And the resulting vector should be u1 plus v1 and u2 plus v2 to un plus vn. Okay. And yeah, well, we have 5 minutes, so we're probably not going into too much detail. But okay, so these two operations are very important. So we are going to see that we are going to give a very abstract definition of vector space, and it will be a collection of whatever things you have, and then you have this scalar multiplication and addition operation on them. Okay. So vector space always have scalar multiplication and addition. Okay. And okay, so let's see a little weird example. This is okay. I keep saying dimension, but I haven't said dimension. But hopefully that's not too confusing. Yeah. Okay. So dimension is going to get a little confusing here. And anyway, so as we say, Rn is a set of all n by 1 matrices, okay, with real entries. So, so those vectors, so once again we call those n by 1 matrix as column vectors, okay, and the vector space Rn is just the set of all of them. And also then you can define the scalar multiplication and addition on them by just the matrix multiplication and matrix scalar multiplication and matrix addition because we view them as n by 1 matrices. And now we can define a weird vector space that has n times n elements. That's just yeah, so we can just view all the n by n matrices as the vector space are n by n. Yeah. So this thing will have n by n matrix, n times n entries. And so how we define, and we can have here we have addition. Okay. So how we define addition on those vectors. And the addition we can once again define by matrix addition. So you have matrix A in this, that's n by n matrix, and okay, yeah. So let's maybe draw a little. So now we have a weird vector space where all the elements inside is n by n matrix. So you have A and you have B. Okay, n by n, and then we say we want to have A plus B, then you just do matrix addition. Okay, and so that will be entry-wise addition. So C equal to Cij equal to Aij plus Bij. Okay. And then you can also do scalar multiplication by just doing a matrix scalar multiplication. Okay. And yeah, so you see this is really R to the n times n because this is just like you have m times n dimensional vector, and you can, yeah, how should I say? The operation you do here is kind of you just view this m times n elements as a really long m times n vector, and you do the corresponding operation, and you get the same result, right? Because you just do entry-wise addition and entry-wise scalar multiplication. Okay. But okay, so that's some digression. But anyway, you can view this matrix is also as a vector space. And I want to go to a little digression and okay, let's maybe not go there. And anyway, so okay, I think we can end probably here. And then we have a very abstract. We can abstract this into a very abstract definition of vector space. Okay. So we say a vector space is just whatever set. Okay. It's a set of any size. Can be infinite size or even finite size. But anyway, and it's a set, but it also from just being a set, you also need two operations here. Okay, so you need to define an addition operation. So addition operation, you will take two things inside the state and give you something else. And there is a scalar multiplication. And yeah, so okay, it's a little more complicated. So you need to define what field your scalar is in. But for now, the scalar, we just say scalar is a real number. It's easier. Okay. And yeah, so it's a set with two operations. You can do addition of two elements, and it should give you something. And you can also do scalar multiplication, where you just multiply whatever element with a real number. Yeah. And then you need to have a lot of property satisfied to call it a scalar vector space. So first, those two operations should have closure property. So you do, yeah. So when you do those operations, you should still get something in your vector space. So you multiply your, okay, yeah. So you have your whatever vector in your vector space and multiply by a scalar, and then you are still in your vector space. And then when you add them together, you still get back something in your vector space. Okay. And as we say, the vector space is set together with this operation. Okay. And actually, the the vector space need to satisfy conditions. So the addition and the scalar multiplication need to satisfy more things. So closure is very basic. Then also need to satisfy all those basic linearity constraints. Those things obvious in the Rn example, but we're going to see we will have a little more strict definitions of vector spaces, and yeah, you need to check all of this. And we are over time, and yeah, so next week next week is no more. Yeah, yeah, next week we will go over chapter 3 again to talk to go into more detail about this abstract definition. And for now, we will have homework on chapter 2, and hopefully you have a good mid-autumn festival. Okay. Yeah. Okay. Any question? Otherwise, that's stuff for now.